Hello everyone, welcome back to DKodeTree. Today I will be solving LeetCode 141 linked list cycle. It is one of the most fundamental linked list problems and is a very important one for coding interview preparation. The problem statement here is very simple. Given the head of a linked list, we have to determine whether it contains a cycle or not. Say in this example, we start traversing the linked list from the head. So we are at 3. In the next step, we will move to 2, then to 0, then to -4. And in the next step, we will again come back to 2. So the easiest observation to make here is, if there is a cycle, then at some point, we will again revisit a node that we have already seen. So the simplest way to solve this problem is to keep track of the nodes that we have already visited or seen, and check if we encounter any of them again. This approach is very straightforward and takes big O of n time, since we may have to traverse through all the nodes before we detect a cycle. However, it also requires O of n extra space because we need to store the already visited nodes in a separate data structure like Hashset, so that we can efficiently compare any new node with the already seen nodes. This approach is very simple to implement, and although this approach is efficient in terms of time complexity, but there exists a more optimal solution which can improve the space complexity. For this, we can use a very well-known algorithm called Floyd's Tortoise and Hare algorithm, also known as the slow and fast pointers algorithm. I will explain both how this algorithm works as well as why it works. In this algorithm, we take two pointers, fast and slow. The slow pointer moves one step at a time and the fast pointer moves two steps at a time. So here the slow pointer is the tortoise and the fast pointer is the hare. Both the slow and fast pointers start at the same position, say at the head of the linked list. And if at any point the fast and slow pointers meet, then there is a cycle. But why does this work? To understand the intuition behind this algorithm, let's go through this example real quick. So initially we have both the fast and slow pointers at the same position pointing at the head of the linked list. So in the next step, we move slow by one step and fast by 2. So now slow is at the value 2 and fast is at value 0. In the next step, we will move slow pointer by 1. So now slow will be at 0 and fast by 2. So fast will move to -4 and then back to 2. Now again we will move slow by 1 and fast by 2. So now slow is at -4 and fast will move to -4 as well. So at this point you can see that slow and fast are again at the same position. This implies that they are in a cycle as per the algorithm. So we know that this example has a cycle in it. Now why it worked is actually very interesting. Let's go back to the first step again, where we have both the slow and fast pointer at the head. Now in the second step, we move slow pointer by 1 and fast pointer by 2. So the slow pointer comes to 2 and the fast pointer comes to 0. Note that while traversing, if there is a cycle, both the slow and fast pointers will be eventually inside the cycle at some point. For this example, at the second step, both the pointers are inside the cycle. We can see that from the diagram. Now, at a point when both slow and fast are within the cycle, say fast is at x distance from the slow pointer. Means we are concerned about the gap between fast and slow. Say as eventually fast can catch up to slow, so we are concerned about the faster pointer to catch up to the slower pointer and not the slower pointer to catch up to the fast pointer. So we are not concerned about this distance, we are actually concerned about this distance and we are calling it as x. So currently we can see that the value of x in this circle is actually 2 because fast is at distance of 2 from the slow pointer. Now what will happen in the next step? So in the next step, slow will move by 1 in this direction, which will increase the gap between fast and slow by 1. And fast will move by 2 in this direction, which is actually decreasing the gap between fast and slow by 2. So 1 minus 2 becomes -1. So the relative movement of fast and slow is actually decreasing the gap between them by 1 at each step. This we can easily see as, say let's move slow by 1. So now slow is at 0 and fast by 2. So fast will move to -4 and then 2, that is 2 steps. At this point you can see the distance between fast and slow is actually 1. So x becomes 1. So what is happening is, at each step the distance x, which is the gap between fast and slow, is decreasing by 1. And as this gap is reducing at each step, so at some point it will definitely reach 0. So let's continue the example. In the next step, slow will move 1 step, so slow will reach -4, and fast will move 2 steps. So fast will move to -4 as well. So we can see that both slow and fast are now at -4 and they have met. So the distance between them, which is x, has become 0 here. So once both slow and fast are within the cycle, whatever the value of x is, at each step it will reduce by 1 and eventually it will reach 0. Meaning the fast pointer will definitely catch up to the slow pointer. Now let's also consider the case where there is no cycle. So let's take an example where we have even number of nodes. So initially both our slow and fast pointer will be at the head. So in next step, slow will move by 1 and fast will move by 2. In the third step, the slow will again move by 1 and fast will move by 2. So in this case, we can see that fast has already reached a null node. So if it reaches a null node, then definitely there is no cycle, as it cannot move forward and cannot reach the slow again. As simple as that. So this we can use as a base condition, that if the fast reaches a null node, then we can return that there is no cycle. In the next case, where we have odd number of nodes, in that case also the slow and fast pointer will start from the head. In the next step, slow will move by 1 and fast will move by 2. So fast is at the third node and slow is at the second. In the third step, slow will again move by 1 and fast will move by 2. So we can see that fast has already reached the last node. But can it move any further? I don't think so, because note that at each step we are moving fast by 2. And after reaching the last node, if we want to move the fast by 2, we don't have anything. We don't even have null. It cannot move beyond null. So that's why we have to stop here, and we can see that there is nowhere where fast can move forward and reach the slow again. So definitely there is no cycle. So in both the cases, where if the fast reaches the last node or any null node, in that case there will be no cycle in the linked list. And we can easily see that if the fast and slow are within the cycle, then they will never reach the null node. And that's the intuition behind how and why the algorithm works in both the cases where there is a cycle and where there is no cycle. The time complexity of this approach is still O of n, because in worst case we may need to traverse through all the n nodes in the linked list to determine whether a cycle exists. But as we are not using any extra space, so the space complexity is only O of 1, and this is where the actual strength of this algorithm lies in. Once you know this algorithm, it's very easy to code up. We will simply take 2 pointers, one fast and slow, as we saw in the approach, and both of them will point to the head initially. Now we'll use a while loop which will run till fast is not equal to none and fast.next is not equal to none. This is the case which is checking that fast has not reached the null node yet, and this is the case which is checking that fast has not reached the last node yet. And we can also omit this part. We can simply write while fast and fast.next both are valid. Once we are inside the loop, we will move the slow pointer by 1. So slow is equal to slow.next, and we'll move the fast pointer by 2. That is fast is equal to fast.next. As we are moving by 2, it's important to check whether fast.next is valid. Now, if both slow and fast meet, that is slow is equal to fast, in that case we will return true, that there is a cycle. Otherwise, if the loop completes without returning true, that implies that there is no cycle and we can simply return false. So this was all the code for this algorithm using slow and fast pointers. Let's run it, and we can see that this is accepted and is quite efficient both in terms of time complexity and space complexity. You can find both the solutions on my website DKodeTree.com. If you found this video useful, do hit the like button and subscribe to this channel for more such videos. In the next video, I will cover linked list cycle 2, explaining how to find the start node of a cycle. So stay tuned.